generalist herbivore, and because it has a wide species distribution, it's been known to consume both macroalgae, turf algae, as well as coralline algae and seagrass. It has been shown to feed indiscriminately on what's in the field, but here in Hawaii, on patch reefs, it's been shown to graze on the predominant algae in the area. Although it's opportunistic, in the lab it has shown preferences. It does prefer the invasive species Haplocycus and does not prefer Coralline algae. This is actually very important because in contrast to other species, Tripneustes doesn't scrape the substratum when it feeds, and so it's assumed to have very little effect on reef infrastructure. And it's important to test if these preferences are apparent in the field as well. Detailed knowledge of urchin movement is essential because their grazing patterns structural algae communities, and which algae urchins feed on and the number of species they have to access is partially a function of the extent and direction of their movements. So this is a question in terms of mobility is to answer if we put a bunch of urchins on a reef where their herbivore is needed, will they stay there rather than dispersing? Field observations have shown that urchins avoid coral and sand, and when you place them on a patch reef in Kaneohe Bay, they have been shown to mostly stay on the reef flat rather than go down the slopes, and it's thought that coral are a partial barrier to their dispersing down the slopes. Maybe perhaps because Tripneustes might be sensitive to those coral polyps and their nematocysts, like me. It's also, but however in pens, when Tamara actually showed that when the algae cover decreases below 10%, urchins tend to escape from the pens more. And presumably they're going to an area with greater food density. So this is a problem if we're looking at them as a biological control agent, because if you're increasing the populations on a reef, you certainly want them to stay there and not immigrate. Previous studies have shown that a very high density of urchins is needed if the algal cover is also very high, about 4 urchins per meter squared. However, this can decrease to 2 urchins per meter squared if most of the algae has been taken off already and it's just suppressing that recovery. The ability to obtain these numbers is obviously problematic because the natural density in Kaneohe Bay is low. Certainly lower than that needed to control at the levels that have been suggested. They're rare in Kaneohe Bay, only really occurring on reefs near the channels. This may be due to patchy recruitment, over-harvesting, and also the degradation of water quality in the bay, which can impact fertilization and also larval survival. However, despite this, the transplanted urchins do survive well. The only way to increase Tripneustes' abundance to a level needed for effective control of macroalgae is by enhancing reef stocks via artificial propagation. They have been successfully cultured and outplanted here in Hawaii. So, while the supersucker has been shown to be an effective tool to remove algal biomass, its mechanical efforts really need to be combined with a biological control agent such as Tripneustes. The enhancement of Tripneustes may prevent subsequent overgrowth of algae on the reefs and allow for the possible return of ecosystem diversity. So my study really focuses on this right here and looking at baseline movement and in situ preferences to determine how these urchins actually utilize a reef that's been cleared by the supersucker. Objectives for this study are to monitor the movement of individual urchins, to investigate the rate at which they sample their environment and resources, examine urchin foraging habits in relation to food availability, with the ultimate goal of providing resource management with baseline movement and field dietary preference data, to aid in determining optimum stocking densities of urchins to maintain low levels of macroalgae on reefs physically cleared of algae. And because urchins have been shown that about 2 urchins per meter squared is effective for the short-term control of an increase in biomass after it's been cleared already, but that's been shown only in pens for a short period of time when the biomass is low. So to really look at on a reef scale, long-term efficacy in terms of stocking density in case urchins immigrant or other factors are affecting their movement. Understanding both movement and preference will provide critical information on the effectiveness of Tripneustes as a biological control agent here in Hawaii. My study specifically asks the questions, are there discernible patterns of urchin movement in the field? Do urchins show preferences for different substrate in the field? And does preference correspond to food abundance? This research was conducted on Patry 44 in the northern half of Kaneohe Bay. The invasive algae Capophycus covers the reef flat and slightly down the slope. In areas that are not covered by Capophycus, crustose coral and algae and limestone predominate. The slope is mostly raised and press up. 1 month prior to this study, the super sucker removed the algae on this reef. So 51 Tripneustes gratilla were collected from reef 13 in the bay, which is closer to a channel, so urchins occur there. Small, white, approximately 1/4 inch, Peterson tags with an identifying number were threaded onto screws and actually screwed into the top of the urchin test, following a procedure by one of the people that actually helped me on this study as well. There is 0 mortality with this tagging technique. In a pilot study, 15 urchins intakes, only 1 tag was dislodged over 9 weeks. That's only a 6% dislodgement rate. Subsequent field trial of 6 urchins all retained their tags over 6 weeks. These urchins were released on the middle of Patry 44, the middle of the area that had been cleared by the super sucker the previous month, about 3 meters onto the reef flat. They were monitored 17 times between March 3rd and May 23rd. About every 3 days, this was tidally driven based on when we could access the reef. However, twice they were monitored on consecutive days. In April and May, they were only monitored about once a week. 2 teams monitored the same area at once, a preference team and a movement team, and they collected data independently. Because we wanted to make sure that each team was able to locate and find the same urchins, teams marked urchins' locations with nails and flagging tape, different colors for different teams. All nails were collected at the end of each survey. To monitor super sucker effectiveness, the super sucker team actually put 12 rebar stakes along the windward or eastern side of reef 44. There's a general description up there in the corner. These reef stakes were going to be used for the movement study. So urchin movement was determined by triangulation using transects. The rebar stakes served as permanent reef markers, and tape was used to determine the distance from the urchin to the 2 nearest rebar stakes. So, in case you're wondering, what is triangulation? I don't remember. Or maybe I've never learned. Here's a primer or review. So for instance, let's say on day 3, urchin number 12 was found in this location. Transects were taken to record the distance between, let's say, rebar numbers 5 and 6. Then 2 days later, on day 5, the same urchin was found in a different location. The distance in terms of transect length was taken from the 2 closest rebar also, and we just maintained the 2 closest rebar because it's easier in terms of the wave motion on the reef. Then, using geometry, you can get the spatial coordinates of x and y, and then once you have the spatial coordinates,